And so it becomes a lot easier doing it that way, but, you know, very few problems actually work out that nicely. But it does happen.
So.
And some people are just comfortable enough with Drake, they prefer this.
Yeah. Are you saying we only use these when we have no exact direction, like 0, 90, 180, 270?
If it's a question of what this angle is. If this angle is not 90 degrees, then you'll be using a lot of cosines, a lot of sines, if
Okay.
you're gonna be doing it from polar form.
Right.
Feel like I missed your question?
No.
Did I answer your question?
Yeah, I
Okay.
mean, kind of.
Yeah, that's why, you wanna try again?
So, what I'm saying is, we'd only use law of are you about to show us a different method with, like, the same exact problem that would be easier? Or are you saying we'd only use law of cosines and sines whenever we don't have an exact measurement with degrees of like 0 or 90?
I'm saying, I would use law of sines, law of cosines, if that's just the way where my head was at that moment.
Okay.
There's no reason why you have to do law of sines, law of cosines for any of these problems.
This was just for demonstration and understanding.
Right.
Okay.
So what's the easier way to do it?
Well,
Nice segue. Right?
no, I'm not sure I call it easier, it's probably a little more steps, what you're about to do.
All right. It is more steps, potentially.
Well,
The work's up front.
yeah, I learned this about 2 years ago, and I learned right triangle trig back in 1981, so.
Okay.
I always run back to the right triangle trig. You know what I'm saying?
Oh, yeah.
The construct another triangle,
There's certain things that I do that flash back to what I did in elementary school.
and that's what I use in the shop.
All right, so the other method is to put them in rectangular form first. So the first one, so I treat them sort of separately. I just sketch out a 5 meters, 37 degrees. I got I hat, J hat defined right here. I'm gonna stick with the traditional boring right and up. This will be 5 meters, 37 degrees, 5 meters, oops, cosine of 37 degrees, and sine of 37 degrees. And this is gonna be somewhere around 4 meters, and this is somewhere around 3 meters.
I have a question about the notation there. Why wouldn't we write 5 times the cosine of 37 meters? Like what,
You're multiplying the hypotenuse times the cosine of the angle. The hypotenuse is 5 meters.
okay, I understand. Okay.
Now, again, it's an intermediate step. I don't
Right,
have to write units here. I know it's gonna be meters.
right, okay.
All right, so this one right here, 4 meters I hat plus 3 meters J hat. Now we do the other one into polar form. So I have 7 meters, 150 degrees. So something like that. That's 7 meters. That's 150 degrees, so this angle right here is 30 degrees. So this is 7 sine of 30 degrees, which would be 3.5. And this is 7 meters times the cosine of 30 degrees, which is somewhere around 6. $6.04. Correct.
I'm sorry, could you explain how you got that 150 degrees in the parentheses with the stuff?
150 degrees is given in the problem.
Okay, got you, so we're still, gotcha.
Yeah, we're still doing the exact same problem we did.
Okay.
Okay, someone got this one?
6.06.
6. There's an alternate way of doing that last bit right there, which I'll talk about in a moment. Just so if you're chomping at the bit of, oh, you could have done it differently. So before we had 6.83 meters, 107.63. That's what we got from Pulver. So once it's in rectangular form, we now write it out. This is 4 meters I hat plus 3 meters J hat plus, what is this in polar form? Yes, thank you, in rectangular form.
6.06, I had.
No, that one's negative.
Thank you.
My bad.
Yeah, that's a critical piece there.
Plus 3.5 meters, J hat,
Plus, what'd you say?
3.5 meters J hat,
Is that what you said before?
yes.
Okay, sorry. And now you add like terms. This is an algebra problem. Yes?
So I'm kind of confused on how, so the problem gives us 150 degrees, but then we're using the 30 degrees, like why wouldn't we use the 150?
It's in the second quadrant, and so using the 150, I'll talk about using the 150 in just a moment.
Okay.
That's, will save a step as long as you don't overcompensate. So now we add like terms, we add the I hat terms, negative 2.06 meters I hat. Then we add the J terms plus 6.5 meters J hat. And now it comes down to, what was the problem? If this problem is add these two vectors together, we're done. We can stop right there, perfectly fine. If I specified I want the answer in rectangular form, well, we're done. And this way we'd have to convert to rectangular. If I said put it in polar form, we're done there, but down here we'd have to go into polar form. Usually I don't specify the final form, but sometimes. So let's go ahead and do these. Let's put this into polar form just to compare it to what we had right there. So we end up with a vector that's going off to the left 2.06 meters and up 6.5 meters. Some angle theta here. And so I'm gonna guess the hypotenuse, it feels like somewhere around 6.83 meters to me.
Yeah, 6.8.
All right, and this angle right here, I feel it's gonna be somewhere around 72.37 degrees. Okay, so we got some rounding issues involved. Forgot what I just said, 72 point, you said 4? 42. Now, so my final answer, if I put this back into polar form, 6.83 meters, somewhere around there. And then, again, if I'm just expressing the angle, I'm from over here, coming all the way around, this is my 72 degree angle, so it's the complement of that, supplement of that. 107.58 degrees. So we're off by 0.05 of a degree. Close enough.
Or we could have been off up there. I think we might have used less decimal points up there as well.
Grading quiz or test, I'm gonna see, yeah, close enough.
I think I missed a step here. Where did you get the 107?
So I created my triangle, going into polar form, created my triangle, so I went to the left, 2.06, and up 6.5.
Right.
This angle right here, I suddenly changed the symbol. The arctan, theta is the arctan of opposite over adjacent, okay, 6.5.
Yeah, okay.
Over 6.06.
Gotcha.
Other questions right now?
I do have a question.
Anna?
I may have done something wrong, but when I did the calculation, I got a negative 72. Are we just getting rid of the negative, or did I type something wrong? Negative 72.4.
When I wrote my triangle right here, I indicated direction with the arrow and I wrote down 2.06. So I was using positive
Instead of
numbers.
writing negative, okay, that's, okay.
Yeah, you ended up with a fourth quadrant angle. As long as you know how to interpret it, that's fine,
Yeah,
but
that's right, yeah, I just typed in negative too. So when we're doing a calculation, when we draw, because it's the force was negative, but the magnitude, the 2.06 should still be positive. So when
Yes.
we draw it out in the triangle, we should just write it as a positive number.
that's the way I do it.
Okay, thank you.
However, seems like a nice segue back to what Loisa said. Why couldn't we have used the 150? In this particular case here, we figured out what's called the base angle, 30 degrees, and then we thought through the fact that there needs to be a negative sign there. We can avoid that. We can eliminate one step of thinking by doing the following. So 5 meters, 37 degrees, plus 7 meters, 150 degrees. If we establish, and this works, given this convention right here, if we pick a different I hat, J hat, different directions, then we'd have to adjust, and then it's no longer worthwhile. This is 5 meters cosine of 37 degrees I hat, plus 5 meters sine of 37 degrees J hat. That's in essence what we did, we just sort of cut out the drawing the picture. Plus 7 meters times the cosine of 150 degrees I hat, plus 7 meters times the sine of 150 degrees J hat. We could have just done it that way, used the 150 degrees. Cosine of 150 degrees is negative, so the negative is going to pop out that way. If you're doing it this method, you don't go, oh, let's see, it's going to the left, so it's negative, but I got a negative on my calculator, so that makes it positive? No. You eliminate that thinking. This will end up being around 4 meters I hat, plus 3 meters J hat, plus negative 2.06 meters I hat, plus 6.5, no, too far, 3.5 meters J hat. And the minus sign will automatically come from your calculator.
As long as it's in degrees.
Yeah. So it's helpful to be able to sketch it out, do the add head to tail. If you sketch it out, then it becomes a little bit more, some mistakes become much more obvious. Questions to hear?
Wait, so basically, I was having trouble like understanding your explanation for why we don't use the 30, but I mean, I was just like suggesting, so if it's over 90, can we just use like, what would, I'm not even trying to say, like, can we just use what angle would make it add up to 180?
The spirit of what you're saying, yes. If I had a 210 degree angle adding up to 180, I would actually find what I needed to subtract in order to get to 180.
So,
Or 0 or 360.
okay.
The base angle is what you're talking about.
Yeah.
And typically, I find I deal with a base angle and then think through where the positive and negative signs go. So that's typically the way I do it. But, well, any computer program, I would do it this way just because I don't have to program in what's positive, negative, the computer knows it for me. Well, you said, did I answer your question?
Kind of like, I'm not even trying to ask it, it's like, cause I'm still figuring out why we use 30 instead of 150.
Because it's the base angle, that's what I needed to get to the horizontal.
So 180, right?
In that case, yes.
Okay.
If I were 300, see, the reason, when you say 180 degrees, it's very specific, and it's really what I need to get to the horizontal. So if it's a 300 degree angle, I only need 60 degrees to get back to the horizontal.
Oh, okay.
So I'd use 60 in that case.
Yeah.
Other questions before I show one other shortcut we can take in some situations?
So what was the answer we were even trying to find?
The sum of those two vectors.
Which was the, you put it in rectangular and polar form there? Okay.
Good, there.
I found myself forgetting that partway through the problem too.
That's why it's being recorded for posterity, so you can cherish that moment over and over again.
Where did the 107.63 come from versus the 0.58 down there? I think I lost where that.
Two different methods that we,
I got you, okay, yeah. So that's just the margin vary between the two?
Yeah.
Okay. Just wanna make sure.
Right. Anyone else?
Well, so our final answer is the 6.83 meters, and then the 107.63 degrees.
Yeah, so our final answer in polar form is this or that, depends on which way, there's
Okay.
rounding off. And our final answer in rectangular form is this.
Our question is gonna ask to put it in polar or rectangular form?
Rarely.
Okay.
The ones that I give, rarely. Textbooks, sometimes they'll go, what's the magnitude and direction of the sum? Which in essence is asking for polar form.
Wait, well, when you do arc-10, 6.5 over 2.06, then you get the 72.42.
Yes.
So then why would you use the word 7?
Because when I go 206 to the left and 6.5 up, the arctan is giving me that angle right there. But when I express in polar form, 0 degrees is over here, and I'm talking about a vector that's pointing like that, so I really need this angle. That 72.42 degrees is this angle.
Oh,
So I need the supplement, I need the 180 degrees minus that.
alright.
Personally, I find rectangular form a lot easier to work with in the long run, but oftentimes in problems. For instance, in chapter 3, we'll get to projectile motion problems, you'll be given the initial velocity in polar form in essence. It's thrown at 50 meters per second at an angle of 40 degrees above the horizontal. All right, so a little bit of a simplification here. We've been dealing with two-dimensional stuff. There's a lot of problems that we'll deal with that were one dimension, especially in chapter 2, a lot of one-dimensional problems. And so we can get away with one conceit. All right, with one shortcut, if it's a one-dimensional problem. We can indicate direction. You can, you don't have to. You can still use IAD if you want to. You can indicate direction with a plus or a minus. So the way I would do it, if I had a one-dimensional problem, that's horizontal, I would just say to the right's positive, and I'd just write that. So if my initial velocity is 5 meters per second, I had, oops, try that one again. In this convention, 5 meters per second, that's that way. And my acceleration, initial acceleration is -2 meters per second squared. That one. And by the way, if these were both applying to the exact same vehicle or object, the object would be slowing down. Not because that's negative, but because those are opposite signs. If we made that negative and that positive, so positive acceleration, negative initial velocity, that object would be slowing down because they are opposite signs.
So, can you explain what you mean by one-dimensional? Cause to me,
Along a line.
okay,
I have a question about, kind of related to what we did in the hall and how we might use this, because it seems like the head-to-tail method creates an endpoint at the end of the first vector that you're adding and subtracting the other vector to. But if they're originating from the same point, like one in the hallway, I could be wrong, but it seems like they're all originating in the middle, like the two forces are pulling out and one is pushing down, so they all have the same start point.
Let's connect.
Huh?
Let's connect what I think you're asking about.
Yeah.
So we had this rope basically like that. We'll take it near the end when Isaac almost had it to the ground. I'll make some numbers up here. So let's say that he was pulling with 50 newtons of force. He was pulling with 50 newtons of force. Some angle theta. Assume Isaac was smack down in the middle and he's applying some force of Isaac. When he has it down there at the bottom, and he's just holding it there, it's in equilibrium, it's not accelerating. Equilibrium does not mean not moving, it means not accelerating. As we'll eventually get to, it also means the total force is 0. So when I add these vectors up, they should add up to 0, which means I should end up back where I started. So I draw one vector here, which represents 50 newtons at whatever that angle that was. Then I add the second one, 50 newtons at whatever angle, that should be newtons there. And then the force of Isaac